Hello APC Mechanics students, today we'll solve the past paper of RQ 2023 Set 2, exercise number 2. Now always remember that the figure happens to be above the text. A student conducts an investigation to determine the relationship between the period of oscillation of a system consisting of a block of N attached springs. The student starts with a block of mass M attached to a single ideal spring. Ideal spring, it means that it obeys Hooke's law, and we can use omega to be the square root of k over m, and the period to be given by 2 pi the square root m over k. And remember, these can be used without derivation, and they are provided on your first sheet of your paper exam. Now the student starts with the ideal spring of spring constant k as shown in figure 1. This is figure 1. Okay, that's the motion detector. The student holds the block so that the spring is neither stretched nor compressed, which means it is at equilibrium. At a vertical height 1 meters above a motion detector, the student releases the block from rest and records the period of oscillation for the system consisting of the single spring and block. An additional identical spring is attached in parallel as shown in figure 2. So after the first experiment, the student repeats the experiment again. Not the student, but the student. So the student repeat the experiment again by placing another parallel spring, and we know that whenever the springs are in parallel, the effective stiffness is given by k plus k, which is k1 plus k2, but in this case it's given by k, so it's the usual sum. And the procedure is repeated for n is equal to 2 springs. This procedure is repeated through n is equal to 10 springs. Now in part A, we need to derive an expression for t as function of n. Express your answer in terms of mkn and physical constants as appropriate. Now remember that the period of oscillation for a horizontal or a vertical oscillator is given by 2 pi the square root of m over k. And this can be used directly. But first, because we're talking about the expression of t as function of n, which represents the number of attached springs, so we need to determine the effective stiffness. Then k effective is given by k plus k plus k n times, and that would be nk. And the reason is that this is for parallel grouping, so it's important that we mention it's parallel grouping. And in this case, the period of oscillation denoted by capital T is given by 2 pi square root m over k effective, which is equal to 2 pi square root m over nk. Now in part B, they're asking us on the following axis, sketch a graph of t as function of n for n is greater or equal to 1. Now remember, the expression of the period determined in the previous part is given by 2 pi the square root of m over nk. So linearizing, or let me isolate the variable n, so that would be 2 pi square root m over k multiplied by 1 over radical n. So the period is proportional to 1 over radical n, so it's gonna be a decreasing function. But notice that we're interested in starting from n is equal to 1, so we're not gonna start from the origin, we're gonna start from somewhere here. So that's 1, and the function will decrease like that. Okay, so this is it for part B. Now going on to part C, they're telling us the student plots the data for t square as function of n to the power minus 1 as shown. Now draw the best fit line for the data. So basically we need to draw a straight line that best fits through all the points. then it's gonna be something like that. Then notice that I have drawn the line in such a way that it passes through out most of the points. Now in idea number 2, before now I continue, and remember this is splitting ideas, which means they are related to each other. Now before I continue, what is the feature of a straight line? And here we're doing a skill which is the linearization. It's basically to determine the slope or the intercept of the curve of the straight line and to determine physical quantities based on that. Now they're telling us the mass of the block is measured to be 1.5 kg. Using the graph, basically we need to determine the slope because we're plotting t-square as function of n-1. Calculate an experimental value for the spring constant k for a single spring. Now before we proceed, let's determine the slope, and here whenever we need to determine the slope, we need to choose 2 points. The thing is that you cannot choose points that are pre-located for us. You cannot use these points to determine the slope of the line because we're doing experimental measurements. So we need to use new points. So I'm gonna use this point, which is here. And I'm gonna use this point as well. Now the coordinates of this point is given by 0.3 and 4. And the coordinates of this point is given by 0.9 and 11. So the slope is basically given by, sorry, let me again. So this is 0.9, if this is 10, this should be 10.5, 11, 11.5. So that would be 10.5 minus, so this is 2, 2.5, 3, 3.5. And the unit of the numerator is given by seconds square. It is important to keep track of the units. Divided by the run, which is basically 0.9 and 0.3. That would be 0.9 minus 0.3. And remember that n, the number of springs, has no unit. Plugging this fraction on the calculator, we're gonna see that the slope is given by 11.67 seconds square. But how the slope would be a feature in order to determine the mass? So the relation that we have determined previously is given by the period, which is 2 pi square root m over nk. Now because we're plotting t square as function of 1 over n, so let me square both sides. So that would be t square, which is 4 pi square, multiplied by m divided by nk. And now we're gonna isolate 1 over n, so that would be 4 pi square m divided by k multiplied by 1 over n. And we know that already the slope is given by 11.67 square. And if you notice carefully, because we're plotting t square as function over 1 over n, then the slope is given by this quantity, and already we know the numerical value and we know the value of m. That would allow us to determine the value of k. So now I'm gonna say that we have, so let me split my space. So we have that 4 pi square m divided by k is given by 11.67. Now we can ignore the units because already we know that the unit of k is newtons per meter. So in this case k, so if we isolate k, we take this up and this down, that would be 4 pi square. The value of m is given by 1.5 divided by 11.67, which means the experimental value of k is given by 5.07 in newtons per meter. Idea number 3, the student finds that the value given by the manufacturer for the spring constant is larger than the value determined experimentally in part C, idea number 2. What's happening here is that we have determined the value of k using an experimental technique. The thing is that on the spring itself there is an indication, and from the manufacturer it happens that the spring constant k is larger than the value that we have determined. Determine a single source of experimental error that could result in the observed difference in the value for k. Briefly justify your answer. So basically, they're telling us to state something that we have done wrong in the experiment that might cause to this difference between the provided value and the experimental value. The thing is that always in experiments, one source of error, this is one source, there might be others, is due to the devices that we're using, and in this case the motion detector. It's not because it is something is wrong with it, but most probably it has miscalibrated before we use it. So our answer would be due to a miscalibration in the motion detector that we have used. But the thing is that because they have mentioned for the spring constant is larger, so a larger spring constant means the period should be smaller because they are inversely proportional. So the period that we have measured is larger than the expected or the real period. So we need to say that it is due to a miscalibration in the motion detector, and we need to state that the motion detector have produced a larger period. So this is important. Then let me say due to a miscalibration, and the motion detector that produces a graph with a larger period that gives a smaller value for k. Now moving on to the next page. Part D, the student conducts a similar investigation to determine the relationship between the period of oscillation T of a system consisting of a block and a number n of identical springs, but arranges the block spring system horizontally on a table, as shown in figure 3. Then what's the difference between figure 3 and figure 2 is that in figure 2, the configuration is set to be vertical oscillator, and in figure 3, the oscillator is set to be horizontal. Frictional forces between the table and the block are negligible. In each trial, the block is displaced the same horizontal distance from equilibrium and released from rest. The students, idea number 1, the students plots t square as function of n to the power minus 1, which is basically 1 over n. For this new data, would the slope of the best fit line from this new investigation be greater than, less than, or the same as the slope of the best fit line in part Ci? Now, if you remember in the previous part Ci, the period was given by 2 pi square root m over k effective. Now the configuration of the springs didn't change. We still have parallel grouping, which means k effective is the same, and the square of the period is given by 4 pi square m divided by k multiplied by 1 over n. So this what we have done in the previous part, and here it remains invariant because we know that the period for both modes of oscillation, horizontal and vertical, is given by 2 pi square root m over k. We didn't change the block, the mass m remains the same. We didn't change the springs that we are working with, so k is the same, which means that the slope of the curve is the same. For this reason, we're gonna say it's gonna be the same as, this is our choice. Remember, even if your justification is correct, you need to state your choice. Okay, so the marks for each is independent. And let me state, since for both horizontal and vertical, oscillator, the period is the same, given by 2 pi square root m over k effective, and we didn't change m or k effective, then the slope of the best fit line is the same. Now, in idea number 2, when we fix the number of n to be 1, the maximum speed of the block is found to be Vmax. Now we're gonna vary n. Will Vmax increase, decrease, or stay the same? So we need to see to check how does Vmax depend on n. Remember that Vmax is given by the amplitude multiplied by the angular frequency. The angular frequency is given by 2 pi f, which is 2 pi divided by the period, and that would be 2 pi divided by 2 pi square root m over nk, which means that that would be given by the square root of nk divided by m, which means that omega is proportional to n, and for this reason we expect that when n increases, Vmax will increase. And let me write it down, or we can directly say that omega, this is not w, this is omega. So first, remember that we need to choose one of these which compensate for a certain mark, whether it's correct or wrong, and you need to justify based on your choice. And sometimes your justification might be correct if your reasoning is fine based on your choice, okay? So always don't try to miss anything out of these. So that would be increase, and I'm gonna say that omega is given by the effective stiffness divided by the mass of the system, which is given by the square root of nk divided by m. Then we know that the maximum speed is given by omega, the maximum position, and that would be the square root of nk divided by m multiplied by xm. Let me write this properly. Which means then when n increases, Vm increase because Vm is proportional to radical n. Then that's it for me in this video, guys. See you soon in a new one.